Hello, everyone. My name is Maggie. It's good to have you here. Welcome to the R&D session powered by EDP. We are the Research and Development Center of EDP Group, and we work on European R&D projects looking at innovative solutions for decarbonization, smartification, and flexibility of the energy sector. The aim of these sessions is to get together experts to discuss several topics regarding the future of energy, the challenges we are facing, and the solutions we are already putting into practice. Please note that these webinars are recorded and the previous sessions are available on EDP's website. You just need to scan the QR code on the slides. Also, this session will be available in our website and YouTube channel in a couple of days. For today's webinar, we have 3 guest speakers that will share their insights with us, so I want to encourage you to use the Q&A chat to ask your questions to them. At the end of the session, we will have a Q&A moment. With no further delays, we welcome you to this event and wish you all a great session, but not without first introducing our moderator, João Gaspar. João Gaspar is a renewable technologies R&D engineer at EDP New in Lisbon, where he focuses on O&M robotics and emerging PV technologies. He plays a key role as both project manager and developer of techno-economical tools, and João is part of the coordination team for the Talus projects. Now, João, the floor is yours.
Thank you very much, Maggie, for the kind introduction. So happy to be here with you all. Good afternoon, everyone, for this R&D session powered by EDP. I'm very pleased to be with you today talking such an interesting topic as the future of solar. So to set the tone for the discussion, as you know, solar energy has had a significant impact on the global energy landscape. We've seen strong growth in solar capacity additions in the last years in Europe, driven not only by climate goals, but also by the technology's economic benefits. But as we look ahead, it's not just about installing more solar, which, by the way, is becoming more and more difficult. It's also about making solar more efficient, more integrated with other activities, and more sustainable as well. And that's exactly what today's session will focus on. We'll explore 3 exciting areas where a lot of research and innovation efforts are taking place, and how they are contributing to advance solar photovoltaics. First, we'll get into the printing of perovskite PV with the Perseus project. So perovskites are a groundbreaking new solar technology that offers the potential for higher efficiencies, lower manufacturing costs, and real flexibility, meaning that they can be bent, which also enables new solar uses, from integrated building materials to portable devices, just to mention a few. Perseus is working to scale this technology from the lab scale to large-scale commercial production in Europe. And we count with the project coordinator, Dr. Thomas Kraft, to take us through this topic. Afterwards, we will look at the life cycle of solar panels with the Apollo project, which is developing a proactive approach to the recovery and the recycling of PV modules. As you know, as millions of solar panels are installed globally, the need to handle their end of life responsibly also grows. And that's where the Apollo project comes in, to ensure that the fast growth of solar then also leads to sustainable resource management and not to future waste issues. And for that, we count on Peter Henach from Fraunhofer to discuss how this challenge might be addressed. And to cap things off, we'll discuss the interesting connection between energy and farming with a global study for agrivoltaics in Portugal, covering the hybridization opportunities and the biodiversity challenges. As you know, the land use is a major consideration for large renewable projects, and in fact has become one of the biggest bottlenecks for the development of new projects. And in this context, agrivoltaics offers a clever solution by combining solar power generation with the agricultural practices on the same piece of land. And so we will count with Diogo Cordeiro presenting this study, which will show how we can create a beneficial relationship between food and energy production here in Portugal. Then at the end, as Maggie mentioned, there will be at the end of the third presentation, there will be a moment of Q&A where you will have the chance to pose questions to all of the speakers. So I invite all of you to write questions in the chat so that we may have a nice discussion at the end. And without further ado, I would like to introduce our first speaker, Dr. Thomas Kraft. So Thomas is a senior scientist and project manager with VTT Technical Research Center of Finland's Printed Intelligence Division in Oulu. He's actively involved in projects related to printed energy harvesting and storage devices, as well as hybrid and structural electronic systems. Dr. Kraft received his PhD from Queen's University in Canada and also the University of Limoges in France. And the work was researching organic solar cells prior to his postdoc in printed electronics at the Tampere University in Finland. Thomas has been an invited speaker at conferences such as the American Chemical Society meetings and the LOPEC, and is also coordinating the Horizon Europe Perseus project. So, Thomas, thank you for being here. The floor is yours.
Thank you very much. What a nice introduction. It's great to be here, and especially with one of our project partners, Zhao. It's very nice to have this opportunity. So today, we'd like to discuss printed perovskite PV, and in particular, I'm going to highlight the work being done in the Perseus project, which is a new EU project that started this year. And let's just get right into it. So as you heard, I come from VTT, the Technical Research Center of Finland. Finland is not so well known for photovoltaics or solar energy, but we do quite a bit of work in the field related to the printed electronics. And that's where the printed perovskites and also printed organic photovoltaics come into play. And especially combining those type of systems into flexible and wearable and IoT devices, those types of things. But in general, VTT is quite a large organization, much more than just the printed electronics. Our printed electronics division is up in Oulu in northern Finland. That's about the 65th parallel or so, just below the Arctic Circle. And that's where we have our roll-to-roll printing lines that we use for instance, for perovskite PV. Our headquarters is though down south in Helsinki, in Espoo, or just beside Helsinki in Espoo. And we're basically a private organization, but we work with both industry and academia to help with innovations, bringing innovations from basically a TRL level or technology readiness level 3 to that technology readiness level 6 or 7. So bridging that gap between academia and industrial development. So Oulu is not always dark and snowy. We do have some sunlight in the summertime. And here's a picture of the city downtown, a core area on the Gulf of Bothnia. And a little bit more about this Perseus. So that's what we're going to talk about today. So it's the project title is the Printed Perovskite Solar Cells for Large Area User Applications. It was funded through the Horizon Europe program, and it started this year in January. It's a 3-year project, and it's co-funded also by the Swiss government and the UK government. And of course, as Zhao mentioned, there's a lot of interest in perovskite PV due to its high efficiency and world records being achieved at lab scale. But the question remains, how can you, again, bridge that gap between academic research or lab scale research to industrial fabrication and large area real world use cases? So that's why we brought together this great consortium of 17 partners stretching from the Nordics through Central Europe, of course, down to the West Coast in Lisbon, and all the way towards the southeast in Turkey. And there are many different research organizations that I'm going to highlight in a few minutes, a few slides from now. But really, it is a combination of research and technology organizations, material suppliers, and end users. What is the concept? Well, as Zhao was mentioning, there is this a lot of interest in this low cost potential of the perovskite PV. Its high power to weight ratio, also its flexibility. So it's an inert, flexible design that can be adapted for various use cases. And of course, this high power conversion efficiency, although it's very challenging to go from the small centimeter squared to meter squared. And of course, it is even more complicated when you want to do in-air or solution-based processing, which we focus on in the Perseus project. But there are applications in floating and urban and agricultural PV, as well as building integrated and building applied photovoltaics. But what are we doing in Perseus itself? Well, so there's 3 different architectures that we're working on for the perovskite PV itself. One is the single junction opaque module. That's with a carbon back contact electrode. So basically you're just shining from one side, being illuminated from one side of the PV device. The other is a semi-transparent module in which you can have a bifacial feature, but also the semi-transparency enables this 4-terminal perovskite CIGS architecture. So these 3 architectures are what we're developing in the project with the research partners and end users. And then they'll be applied in real-world demonstrator sites for floating PV concepts, a building integrated PV approach, agri-photovoltaics, and also urban integrated photovoltaic. And then, of course, we're assessing the performance, lifetime, and cost requirements that are needed for these. And of course, you're probably already wondering, well, of course, there's the stability issue of the perovskite that's being highly investigated within the project. And that, of course, relates to encapsulation and these manufacturing processes for interconnections that go hand in hand, basically. And here is the value chain of the perovskite work and manufacturing that we're doing in Perseus. Of course, we have very important players that are sort of outside the direct technological development. This is a Phoenix TNT for dissemination, exploitation, and communication. We have Iconic Innovation for tech analysis and future funding. And then Oxford Brook University from the UK for basically the life cycle assessment, environmental and social impact. For our knowledge transfer, VTT, we're working a lot with the roll-to-roll gravure printing and also the interconnections, and so manufacturing of the PV system integration. Fraunhofer is working on substrates and barrier foils. TNO, a specialist in slot die coating, working on various curing and annealing methods. Helmholtz Berlin, there's a digital data platform for open source sharing, but also for internal project collaboration for data management. And ODTÜ Gunam from Turkey for different new materials and interfaces within the perovskite stack. Material developers like Soleveni from Germany, Dicotech from the UK, and Avantema from Switzerland also play critical roles in improving the material, not only material availability or selection or synthesis of the materials, but basically the inks that need to be used in the manufacturing processes. So, of course, the formulation of these inks. And then supplying these to our end user, Saule, a PV a PV product manufacturer. And then there's Fusion Bionic from Germany as well, where we're working with basically different texturing and optical properties of the PV plastic materials. And then we have our end users from industry, and of course EDP working on those application use cases, including Midsummer, and that's for the CIGS manufacturer, of course, for the 4T tandem. Then we have Ocean Sun and Polysolar, and then, like I mentioned, EDP. To give you an idea of what I mean by the printed perovskite, many of you might not be so familiar with this, but these are examples that we've done at VTT on our roll-to-roll lines. I would say about 7 or 8 years ago, we started to work on this. And it started off with this 2-step approach. What I mean by that is you print a precursor, then in another step, you'll print then the next component of the perovskite, and then you go through a crystallization bath. And this separates the processes to have very controlled crystallization of your perovskite active layer. Another approach we used was a one-step with an anti-solvent bath. So you print both precursors at the same time, and then it goes through an anti-solvent bath. Although these anti-solvent baths are not ideal, especially when you talk about volume manufacturing. So what we're trying to do is get away from that. So at VTT, we don't use any anti-solvent bathing, and we do a one-step approach. And in this case, we need to really have a very well-controlled ink and ink formulation to get that good crystallization and controlled crystallization growth of the perovskite during the in situ printing process. This is an example of one of our roll-to-roll lines at VTT. Here we're printing the NIP architecture with a back contact carbon electrode. And this can also be replaced by evaporated gold for sheet-based testing. But what we do is we have a roll of ITO that we receive from a commercial supplier. Then we do a roll-to-roll wet etching of the ITO. And then we do roll-to-roll gravure printing of the electron transport layer, this ETL, which is commonly a tin oxide. And then we gravure print the perovskite formulation. This is followed by, of course, by annealing, and then gravure printing the whole transport layer, which is a very good workhorse for us, is the P3HT, poly-3-hexylthiophene, which if any of you know organic photovoltaics, you might be familiar with this. And then we'll print this rotary screen print, the back carbon electrode. After module printing, we'll encapsulate it. We have a roll-to-roll encapsulation line. And here's an example of one setup we have within the consortium. This is being developed at VTT, but of course our other partners throughout Europe, they have their own testing sites, and we utilize those in the project. But this subarctic outdoor test, I wanted to just mention, especially for those from Portugal and from the south, that we do have these facilities that we're developing in the north. This is the most northernly flexible perovskite outdoor test facility. And it's, like I mentioned, it's in Oulu at the 65th parallel. In the winter, we get about 3 hours of sunlight, but it's not real sunlight, it just sits on the horizon. And then in the summertime, there's about 22 hours of direct sunlight. So it's a very variable system, and something we're very interested to see in the long term, how the PV devices, and particularly the flexible perovskite PV, can handle this. Because, of course, you've probably heard of some of the aging, even daytime aging effects and nighttime repairing of the perovskites. Here's just an example of one test case that we have on the roof. It's just an overmolded amorphous silicon sample, but you can just see how you get these nice curves of illumination. You can see there's some cloudy days in this sample, but I just wanted to show this to show you that it is functioning, and we'd be very happy to discuss with you if you're interested. As the project progresses, like I mentioned, we're only at M6, month 6 in the Perseus project, so things are really starting to pick up pace, and we've done a lot of work so far. But the key large area printing and outdoor demonstrators and real world use cases are still to come. So I really encourage you all to stay in touch with the project, and please follow us on LinkedIn, and you can visit our website and contact me if you have any questions. But thank you very much, Zhao, and everyone for listening.
Thank you very much, Thomas. Very interesting presentation, and quite impressive technology. This will be quite interesting to follow up how it evolves and how we can scale this into large-scale modules. If you have questions, just a reminder, please write them down in the chat. We will have a dedicated Q&A session at the end. And in the meanwhile, I will be sharing again my screen to present our next speaker, Peter Henach from Fraunhofer CSP. So Peter is a scientist at the Fraunhofer in Halle in Germany, working in the research area of recycling. After having received his master's in chemistry at the University of Leipzig, Peter has focused his work on the analysis of recycling material, as well as the optimization and development of processing routes. He's worked in the publicly funded project Remodule on the recovery of silicon from end-of-life PV modules to produce new solar cells for a new PV module as a demonstrator. Peter, thank you for being here with us, and the floor is yours.
Thank you for the introduction. I just share my slides. And yeah, as we have seen, my name is Peter Hinnertz. I'm from Fraunhofer, as you already introduced me. And in Apollo, in this project, in the EU-funded project, we try to address the problem with the PV waste, the coming problem with the PV waste. So our motivation is, we all know there's an increased capacity of PV modules, of the installation of the PV modules, and it's increasing, and we will expect the PV waste to come back 20 to 25 years later. So it's quite easy to roughly calculate the expected PV waste. So as we can see here, in the beginning of the 2030s, we will expect 1 to 2 million annual tons of PV waste just in Europe. And if you look in the global world in the beginning of the 40s and even over the 30s, we will expect up to 10 million tons of PV modules annually. And our approach to address, or we want to address this PV waste and this challenge and give it a try. So the key issue at the current recycling process is that mostly they are just focused on the aluminum frame and the glass and the wiring. And after they recover these materials, the remaining material is mostly thermal treated or burned off somewhere. So all the silicon and silver which is contained in the PV cell is wasted. Our vision is to create a real circular economy for the PV modules. We use all of the materials back into the PV industry and boost the material recovery of these processes we are experimenting with to rates above 90%. So in the end of the project, we will construct a pilot line in Germany where we can process up to 40 tons of PV waste to reclaim enough material, 1 ton of silicon, to produce new PV modules and also tandem modules from recovered perovskite cells. So in total, our objective, or we constructed 6 objectives for our project. First of all, we want a pre-recycling analysis of the PV modules before we send them for the processing, just to distinguish the modules in their antimony content. Because if we use glass with lower antimony, we can go into different glass markets than with glass with a high antimony content, where we only can go more or less back into the PV market of pressed glass sheets. So the second objective is to produce a pilot processing line to extract all of the material fractions of the PVs. So really address all of the fractions like silicon, silver, aluminum frame, glass, polymers, and so on. Then this recovered silicon has to be further purified. There our colleagues from Norway, from SINTEF and NTNU comes in place. They have the thermal process to purify the silicon, to purify it to a stage where we can use it for new ingot growth and for new PV. And the fourth stage, there's a remanufacturing of these recycled materials to produce new tandem cells, but also standard crystalline silicon PV modules. And the fifth objective is to develop an implemented digital product passport and also an online marketplace for the recycled materials, but also for second life modules or for the recycler itself. And the sixth objective is to develop and quantify this and promote a new circular business model for the PV waste, that really all of the PV waste is used and not just the more or less low-hanging fruits of frame, glass, and cable. So more or less, our project is structured into 5 processes. So we start with the sorting and crushing more or less of the module, then the extraction of the metals in the module, the refining of the fractions, reusing of the materials, and also and last point, the tracing and circularity of all these modules and materials. In the sorting, we are now removing the frame and the junction box and then shred these modules after they have been tested by our colleagues from IPN for their antimony content. Yes, this laminates or the deframed modules are shredded, and you can see here some fractions will get produced via electrostatic or electrical conductivity separation or density separation. So we can get down to the silicon or the cell fragments at this stage, and some class particles here are shown some small particles, but there are also the larger particles from the shredding process and some polymer fractions. For the extraction, we plan to recover 93% of all the material types in the cell fragments. So therefore, our colleagues at Leicester and Glasgow are using a deep eutectic solvent and in combination with ultrasonic ultrasound to recover silver, copper, tin, and lead from the cell fragments. And actually, I think within the last meeting, they also presented there's a full circle which they can run with the deep eutectic solvent. So they could achieve to recover the silver from the solution and reuse the deep eutectic solvent in the same process once again. And so they can minimize the environmentally harmful and toxic chemicals, which are commonly used, like nitric acid or something in this direction, to recover the silver from solar cells. Yes, in this picture here, you can see a rough sketch of the planned pilot line for this process step. So it's more or less a tube with the ultrasound generators around it, and the crushed PV suspended in the DES will get led through this tube to recover the silver, copper, tin, and lead from the PV cell fragments. Then we have the part of the refining after the extraction. We still have the silicon leftovers, but to reuse it in modern PV modules, we have to keep in mind that there was a shift in the silicon from P-type to N-type, or in the production of solar cells from P-type to N-type. So we also have to get rid of the dopant inside the recovered silicon. And that's where the colleagues from SINTEF and NTNU in Norway come into place. They are using this metallurgical process where they are using vacuum refining to remove the phosphorus, and in the second step, some gas purging to remove boron and also some smaller remaining impurities which could not be removed during the extraction of silver, copper, and tin and lead. Yes, here you can see some picture of the used furnace and also some first experiments they have done. At the moment, they are scaling up these processes to process larger amounts for the crystallization, which has to come in the project. In the fourth stage, then we are planning to reuse all these extracted and purified materials to produce 20 PERC-based crystalline silicon modules, 10 tandem modules based on monolithically integrated cells, and also just some standard perovskite cells. Here, the colleagues from Kalyon in Turkey will produce crystalline silicon modules. And again, as in the presentation before, Solarveni is involved here for the perovskite and also the tandem modules. And in the last point, we want to implement a digital product passport and a PV marketplace. So here, the colleagues from MindSpider and also from Swansea University developed this digital product passport, where all the materials, more or less, the quantities, the dopants, a lot of data should be involved concerning the the module, but also the lifetime data of the module. So more or less at any time you can say, what is the status of this module? What is it worth? Is it worth for recycling, and so on? And all these topics which are involved, relevant for the recycling or even the second life use. That's also where the marketplace comes into place. There we aim for to open this marketplace for second life modules, but also the recovered components from old PV installations, recycled materials from the PV modules, but also for recycler and their capacity to show what they can do, and also that they still have capacity and can deal with more PV modules. At the moment, these two parts are in internal testing, but as I heard from my colleagues from MindSpider, I think at least the digital product passport is quite far already and ready for open testing, I think. Yes, now I talked a lot about our partners already. Here you can see a nice view over Europe with our 18 partners from 9 different countries. So as I already mentioned, NTNU and SINTEF from Norway. We have Calgon from Turkey as a PV producer. We have MindSpider from Germany, which are working on this digital product passport. We have Phoenix again, which is more or less working for publication and organization. IPN from Portugal, considering the class analysis. Then also we have the NSG group with Pilkington in UK for the class reuse more or less in a float class process afterwards. Yeah, and so on and so on. In total, at the moment, we are in halftime with this project. So we started in January 2024 and will be hopefully finished at the end of next year. We are co-funded by the European Union as well, but also from the Swiss State Secretariat and the UK Research and Innovation. And yes, we hope with Apollo we can improve the recycling practices for photovoltaic waste, and really create a circular approach for all this waste, which has to come in the next years. And thank you for your attention.
Thank you very much, Peter, for the presentation and for the insights about the scale of the challenge that we have facing us in the next coming decades related to recycling, and also letting us know about the proposed methodology that you are exploring in Apollo. To cap off the presentations, I would like to introduce Diogo Cordeiro from EDP. So Diogo has 18 years of experience in the energy sector as a project manager for continuous improvement programs, innovation and technology initiatives, training management. He has participated, been part of the EDP Lean program, EDP Corporate University, and also EU funding innovation programs. Currently, Diogo is a project manager at the Renewable Generation Assets Platform, and aiming to identify and test new technologies that could help new business growth and operational excellence. Okay. Can you still see my screen?
I start sharing my screen. I don't know.
Okay, perfect. Perfect.
You are seeing my screen.
Diogo, welcome. Thank you for being here, and feel free to go ahead.
Thank you. So you are seeing my screen, correct? Okay. So hello to all. Thank you to EDP for the invite. The study or the summary of the study I'm going to present is a consortium or that EDP Produção in the former organization of EDP challenge Universidade de Évora and EDP-NU to study a new tech that we want to start deploying. And the 5 slides that I have are more or less the short summary of the study. The beginning of this starts with OTGen. OTGen is an observatory that EDP production or EDP generation had in the past when we want to study promising and new technologies, just like the storage in a decade ago, the floating PV, the hydrogen, and so on. So the trending technologies that we are not introducing within our assets, we start studying typically with the OTGen forums. And one of the trending technology that we've identified in the last years was agri-PV. And the reason of that is because we have a lot of hydro and thermal assets near agricultural land that they are possible to hybridize. And the challenge for EDP-NEW and Universidade de Évora was study the land that we have. We invited EDP Renewables, and in the meantime, the organization changed, and now the EDP Produção and the EDP Renewables are renewable generation assets. So the results I'm going to present serve for both companies. One conclusion that was a starting point, and we know, is that agri-PV is not a one-size-fits-all solution, as it was the conventional PV, in which we have land, we have structures, we could have a kind of a guideline to optimize the construction and the operation. In agri-PV, that is more difficult. We could have some guidelines, but it's not possible in the short term. So what we know at the beginning is that we have a lack of regulatory legislation in Portugal and in Spain to deploy agri-PV. We have some constraints regarding the specific zones for agriculture. We know that the design and the costs will be higher because we have more structures than we have in the conventional PV. And we don't have yet, at the beginning of the study, some well-defined business models. So what we try to study is if we want to create a roadmap to deploy agri-PV, or if the rules change, what we could do. The first point was to specify what is agri-PV. In US or outside Europe, agri-PV could be PV plus typical agriculture or animals. In Europe, typically, the agri-PV definition is sown only with agriculture production. So we try to check in this definition, more close definition, what are the structures, what are the methodologies we could use. And they are essentially two types, the overhead and the interspace, that they are that have synergies with the conventional parks we have. And on the right side of the slide, you could check we have overhead solutions till 2 meters for vegetables, and you could have till 4 meters for trees and trees and cultures. Other possibility is interspace. And interspace, for instance, have synergies with our parks. We could have a park with a higher dimension, but when you cultivate in the interspace, and we could have this interspace with a kind of angle, or it could have completely vertical, as in this example. For other sides, and for instance in Portugal, we have a lot of greenhouses, and this is a solution that could use too, but more for the retail than for the generation units. Another point that is important is to specify the KPIs and the stakeholders difference when we compare to a conventional PV park. We have more KPIs when we try to decide if a park, agri-PV park is profitable for both sides, for the utility, for the investor in energy, and for the farmer. We have KPIs just like water use efficiency or water access that we don't have in conventional parks. We have the agriculture production costs. So we have a lot of inputs that we need to put in the mix when we try to calculate the profitability of the investment. However, the farmers we interview and do some workshops, they are very open to be partners for agri-PV. However, they have typically the same. They are afraid of the same thing. One, because the agriculture in Europe is very subsidized by European Commission. What they tend to be afraid is that if they deploy agri-PV, if they lost the compensations from the European projects or the European funding for agriculture. And other point is the access to the grid, because some farms are very far from the grid connections, so the cost of the park is higher or will be higher due to new grid licensing. And for other side, that is obviously they want that to be more profitable in terms of agriculture. However, what we study and what we identify is that all the business models that are here, these 5 that could be merged in 4, all of them are profitable for both utility and farmers. However, there are some conditions we need to check to have. So we don't have so many land in which it result quite good. So we have a kind of a niche in Portugal, but is a niche that could be sufficient to achieve the goals of renewables that we define in our national plans. So the business model are utility as landowner, and we want is a kind of a partnership with a farmer. The farmer and or other landowner as the owner of the land, and utility is the operator and the OEM for the park, a turnkey contract in which we sell the project, or energy community, that is a business model that is easily adapted by the commercial solutions or the retail platform of the utilities. So the main takeaways is that the farmers and utilities have here a good business opportunity. the B2B have some constraints regarding the current legislations in terms of energy communities, but the farmers could have huge advantages because they have discounts in electricity bill, water savings, protection against weather conditions, and in some, just like producing wine, this is one of the points that could be a good opportunity because the land must be prepared for extreme weather conditions, and the PV could be a first barrier to that. And there are a new possibility that was presented, for instance, by APREN, that is the sustainability certifications for those who deploy an agri PV project, and the farmer and the utility could sell that certificate as a totally green product, agriculture product. So to summarize and don't take more time, the most important conclusion is that to deploy in Portugal and even in Spain, we need to have some crucial changes in terms of legislations and in terms of agriculture legislations that create barriers to deploy new parks. Even these parks are completely sustainable and they are mainly for agriculture. Other point that I pointed before is that agri-PV is more complex, is not a one-size-fits-all solution, but we have currently in the market solutions to adapt for most of the needs of the farmers. The other point is that agri-PV is more suitable for new land than for the current ones, but there are possibilities. And the last one, that is the point in which EDP is right now in Iberia, is that we need further analysis to progress that. So we need to piloting that as soon as possible in some land, and we, with some partners, are trying to do that, just like other utilities are doing. Galp is doing that, Iberdrola is doing that. So the utilities are testing solutions. So this could be a trend in Iberia in the next years, and is right now a trend in all Europe. And thank you for your patience.
Thank you very much for the presentation, Diogo. Very interesting to hear more from the utility side on agri-PV. I believe it's time for questions. So we have been noting some questions that the other participants have been writing. I would maybe start with Thomas. So on the perovskite Perseus project. Question from Umberto. We would like to know more about the mechanical resistance of these kinds of panels. Do they receive a glass frame over them, and how do they behave under mechanical stress?
Yes, that's a really good question. And I think the beauty of the flexible PV is, of course, to try to avoid the rigid structures of frames and, especially of a glass covering. So one alternative to flexible barrier films for encapsulation is you can actually, of course, encapsulate with glass directly, or you could have the PV module encapsulated with the barrier film and then subsequently encapsulated between glass sheets to be applied in, for instance, in rooftop applications. That is a very mechanically robust technique. But one thing we're trying to do in Perseus and in other application areas is to avoid the rigidity of the glass and to have high performance barrier films that can withstand environmental aging. So have very high very low water vapor transmission rates, but also have high durability under UV, thermal stress, and mechanical stress. Other ways to improve the performance of the flexible PV is to have these optical hard coats as well, to have other properties within the on the plastic surface to avoid bacterial growth and these sort of things. These are all being developed. So I hope that addresses the question. I think it's yeah.
Yeah, no, I think it does. It's good to know that we can somehow tune the robustness of our module according to our needs, either if it's more flexible or more rigid in this case. Thank you, Thomas. We have a question as well for Peter regarding recycling. And actually, I think I will ask two questions at once, if you don't mind, Peter. One of them is from João, so mentioning that the great majority of PV is being produced in China. Do you know if recycling is already a concern for Chinese manufacturers? Are there any examples of materials being incorporated back into the value chain? And then also a question from Nuno. What do you think the role of manufacturers should be in improving the recyclability of PV modules?
Yes, so coming to the first question, yes, recycling in China is also starting to develop. They have to deal with these manufacturing scraps, so they always have a lot of modules which are not working as expected from the manufacturing, so they have to recycle these modules at least, so they have a growing recycling capacity. And also, if you look into the patent markets, there are a lot of patents from Chinese companies which at least try to address this recycling problem for them. We always have to be careful, so I don't really have details. I haven't seen the machines there. I have seen some videos and it looks quite rough, the recycling, I would say. But I think it's a developing market, and as we know, the Chinese, they are quite fast in developing this, if we see the PV manufacturing as well. So yeah, I think they see this recycling problem coming and are doing some development. And the second question was
it was regarding the role of manufacturers in the recycling process. If they should be the ones responsible, or if it should be other companies taking care of this.
So actually in Germany, it's more or less manufacturers who are responsible for the recycling and also for the for the costs of the recycling, or not just the manufacturers, but also the traders who bring the PV modules on the market in Germany. I'm not quite sure how it is in every country in the EU. But if you look more into the field of design for recycling, as I understood this question in the chat, I think it's also complicated because all of the manufacturers, or most of the manufacturers today, are located in China, and we don't really have a huge influence on this point on them. So we have to see that we get it somehow in legislation to get a more recycling-friendly module. And on the other side, for this design to recycle, we always have this conflict of lifetime versus recyclability. So sometimes an easier to recycle module has a lower lifetime, and yes, that would be a
very
problem.
clear, Peter. Thank you. I would maybe pass the word now to Diogo. So a question from João. In your opinion, what are the regulatory changes that you anticipate that could support the broader implementation of agrivoltaics in Portugal and across Europe?
Okay, so in Portugal, we are not allowed to deploy PV investments or in Rede RAN, Rede Agrícola Nacional, in the agriculture national network or grid, and due to that, there are the best land to produce agriculture are reserved so only for the agriculture purpose. And with that, the land that is not so good for agriculture purpose, that the one that we have available right now to that. If you want to deploy with a big farmer that has his land in RAN, we are not possible to do that right now. However, there are some conversations and some public speech from the current government that want at least to discuss this topic. In Spain, what they did was create a kind of a tariff for the for agri-PV that they pays very well the energy, so the investment and the risk. And in other countries, and this is the second part of the question, in other countries, just like in France and Italy, that are clear constraints to deploy conventional PV. And due to that, the investors, the utilities, change the approach and use agri-PV as an alternative to validate and to have to deploy PV capacity. This is an alternative. This is a trend that European Commission already discussed, and may you know, some regulations that were approved by European Commission then tend to be approved in the countries. So it could be a possibility. If there is a clear guideline by European Commission, Portugal may need to obey that, and you could have opportunity for deploy agri-PV. However, the problem is that typical this kind of regulation are more not in favor of conventional PV, and the agri-PV is an alternative to continuing the business.
Yes, I understand. Diogo, maybe another quick question for you. How do you assess the different the comparison of the LCOE of agri-PV project with conventional PV projects?
We did some calculations for the study in Portugal based on the land we choose. That was very good in the south of Portugal, and we don't have a huge investment in terms of grid. So the LCOE, or the theoretical LCOE we have for our pilot was good, even a bit higher than conventional PV, but lower than floating PV. So in terms of alternative or non-conventional PV, agri-PV is slightly in the middle of the conventional and floating PV, because the cost of OEM of agri-PV are not so higher than it could be in the floating. Even the structure of the agri-PV are more or less the same, but a bit higher. But when we try to invest on this technology, we are not technology or methodology. We are not thinking only in LCOE, because it's a symbiotic project with agriculture. So if we have a farmer don't have profitability with that, it is not possible to have a functional agri-PV. And without cultures, there are more sand, there are more not controlled vegetation, and the cost of OEM increase. So we need to have a kind of a partnership in which the agriculture profitability increase. In some cases, we need to share some of our profits in terms of electricity with the farmer, because it's an important part even for OEM, and because of that, we could have profitability not only in terms of the conventional part of the electricity generation.
Of course. Makes sense. Thank you very much, Joe. We are quite short on time, but I would like to put just one final question, and actually that touches on both topics of Perseus and Apollo. So what are the main challenges in recycling perovskite-based modules compared to traditional silicon modules? Thomas and Peter, feel free to comment on this.
I can comment. Actually, there's a lot of work on this, and I'll put a publication in the chat. Actually, it was from a few years ago, but my colleagues at VTT and some researchers from FHNW in Switzerland and some other institutes in Europe in a common project. So of course you can extract materials of the active materials from the perovskite devices. It is possible. The amount of material waste, the amount of material though in these thin film PV devices is quite small, so you need a large supply to effectively extract the material of choice at the expense of the valuable materials. They need to define, are those materials worth extracting? Of course, in some cases it is needed, but for instance, these plastic-based modules, they can be shredded, and then you can do solvent extraction of elements.
Thank you, Thomas. Peter, any very quick comment on this? We need to close the session.
Just a quick comment on the lead content. If you really just shred them in a tri-stage, more or less, then you also have to keep in mind that you have a huge lead contamination, more or less, and you have to apply the correct safety for your workers and everything. That's something to keep in mind as well, or just shred it underwater.
Thomas, Peter, Diogo, thank you very much for this very interesting discussion. Maggie, thank you as well for the organization. I give you the word.
Well, I just want to close the session. I want to thank our speakers for accepting the invitation, Thomas, Peter, and Diogo. I think it was really interesting and it was really engaging. So thank you for accepting to be here today. The R&D sessions will return in a couple of months, always powered by EDP. So let me just say to all of you to enjoy your day and hope to see you in the next session. Thank you.